do a chem quiz yesterday. My mom decided to put it to today, which was actually better for me, so I'm not complaining. And then I made that. Because that means I got to study last week.
All right. So today we're going to look at one-sided limits, which is something that we have talked a little bit about. I've mentioned it. So let's see how this works. Consider that function. And you can see it's defined by two different equations depending on what the value of x is. It's defined by y equals x squared when x is less than or equal to 1. And then it's defined by x minus 3, which is the same thing as negative x plus 3. By writing it in this form, it's slope-intercept form. And that is true when x is greater than 1. So if you want to find f at 0, because that's less than or equal to 1, you'd have to use the first equation. 0 squared is 0. If you wanted to find f at 1, again, you have to use that first equation because that is used when x is less than or equal to 1. 1 squared is 1. But for f at 2 and f at 3, because now x is greater than 1, you're using the second equation. And you've got those values. So as it says there, we can investigate the limiting behavior of f at x as x approaches 1. So using a table of values, as x gets closer and closer to 1, but below, so you're going to use that first equation, you get values of f at x that also approach 1. And then notice how this is written. The limit as x approaches 1 negative. And what that means is approaching 1 from the left side of 1, using values that are smaller than 1. So the value of that limit is positive 1. The table of values shows us that. From the right, you can see that the values are approaching 2. And so we say the limit as x approaches 1 positive, which means the right side of 1 of f at x is 2. So therefore, the two-sided limit, the limit as x approaches 1, does not exist. Yes?
So this is for a graph that goes like this.
It'll be it's a different graph altogether. I mean, if you look at it, the first graph is a quadratic, y equals x squared. The second one is a line.
But like in the previous chapter or previous lessons, we learned about like the limit does not exist in the graph will always looks like this for it's approaching the
That's one example where the limit doesn't exist, but this graph will not look the same. Okay? It won't look the same. So again, the two-sided limit does not exist because the function approaches different values from left and from the right. And we'll see the graph, see what it looks like. So when x is less than or equal to 1, it's defined by y equals x squared, which is a quadratic. A quadratic that would go through 0, 0, negative 1, 1, negative 2, 4, and it goes through 1, 1, and that's the last point on that quadratic, because the quadratic is only valid when x is less than or equal to 1. So this graph will look something like this. Yeah. Okay. Okay. No problem. Now, when x is greater than 1, it's defined by negative x plus 3. That's what we said we would write that as. So that would be a line that would have a y-intercept of positive 3 normally, and a slope of negative 1. So rise 1, run 1. Now, rise negative 1, run 1. Now, if I rise negative 1 and run 1, it takes me right there. But that would not be a point on this graph, just like the y-intercept would not be a point on the graph, because this graph is only valid when x is greater than 1. So that's why I've drawn an open circle on that point, because it's not included. Now what do we do, Brighton? I know you're not really sorry, but... Okay, good. So we'll keep rising negative 1 and running 1. keep rising -1 and running 1, and this gives us the points on that line. So now we can draw that. And this graph would look something like that. So again, we did it with the table of values. Now we're doing it graphically. We can see that as x approaches 1 from the left, the graph is approaching this point here with a y value of 1, which is y, and the table of values showed us that. The value of the limit as x approaches 1 from the left, or 1 negative, is positive 1. But when you approach 1 from the right, you're getting closer and closer to this open point with a y value of 2. And that would be the value of the limit as x approaches 1 from the right side, 1 positive. So, again, we can say that in this case, the limit does not exist because the graph is approaching different values from the left side of 1 as it approaches from the right side of 1. So we can state the limit as x approaches 1 from the left, we can state the limit as x approaches 1 from the right, but we can't state the limit as x approaches 1 because it does not exist. Okay? So if the limit as x approaches a from the left of f at x does not equal the limit as x approaches a from the right of f at x, then we say the limit as x approaches a of f at x does not exist. But if they do approach the same value, if the limit as x approaches a from the left of f at x is L, and the limit as x approaches a from the right of f at x is also L, then we can say the limit as x approaches a of f at x is L. Yeah.
Question never asked Mrs. Long what limit is the right side.
Yeah, and that's the very next question.
Oh.
So yes, you will be asked to evaluate one-sided limits. So determine the limit as x approaches 0 from the right of the square root of x. Now, this one is somewhat redundant because you cannot evaluate that limit when x approaches 0 from the left, because that would mean that x is negative, and you cannot take the square root of a negative number. Okay? But we're still going to do this. Note that this is a one-sided limit because x is greater than or equal to 0. And so the table of values shows us that as x gets closer and closer to 0, f at x will also approach a value of 0. And so that's the value of that limit. And a graph can be sketched, and we can see that as x approaches 0 from the positive side, the root of x approaches 0. So therefore, the limit as x approaches 0 from the right of root x is 0. And you might remember what the graph of root x looks like. You spent time in 30-1 looking at it. Starts at 0, 0, it goes through 1, 1, and 4, 2, and then actually 9, 3. And it goes on forever. As x increases, y will increase. X will increase at a faster rate, but y will continue to increase, so that graph never flattens out. It's always going to be rising. Okay, so whether you use a table of values or you look at the graph, they both show us that as x approaches 0 from the right side, that function is approaching a value of 0, so that is the value of that one-sided limit. So let's look at this one. This equation has 3 parts to it, again, depending on what x is. So the first part is that the function is defined by negative x minus 2 when x is less than or equal to negative 1. So negative x take away 2, that's a line in slope-intercept form. It has a y-intercept of negative 2 and a slope of negative 1. So y-intercept of negative 2 and a slope of negative 1. So we'll rise down 1 and run 1. We'd rise down 1 and run 1. So this would give us points on the line. However, in this case, we cannot use this line unless x is less than or equal to negative 1. And x equals negative 1 over here. So I need to generate some points going the other way on the graph. I'm going to rise 1 and run negative 1. And so that'll be that point right there, which will be a point on the graph. Because this graph is valid when, or this equation is valid when x is less than or equal to negative 1. So that would actually be the first point. If I rise 1 and run negative 1, rise 1 and run negative 1, that gives me a few more points. So now I can draw this part of the graph. Okay, it looks something like that. These other points, we can get rid of them because they're not part of that graph. This part of the graph is only valid when x is less than or equal to negative 1. Now we're told that the other part of the equation, or the next part, is that y equals x when x is greater than negative 1 and less than positive 1. So the graph of y equals x means that x equals y. Whatever x is, y is the same value. So it normally would go through negative 1 comma negative 1 because that point has the same x and y value, but it's actually not part of this graph, it's part of the first one. But this graph would go through 0 comma 0, and it would go up to the point 0 comma 1, or excuse me, 1 comma 1, but that's not part of this graph because, again, this graph is only used when x is greater than negative 1, less than positive 1. So this part of the graph looks something like that. Now, normally this point here would be an open dot as well. It's not part of the graph we just drew, but it is part of the previous graph, which is where these two graphs intersect. So that's why there's a closed dot there. It's a part of the first one, not a part of the second graph, not a part of the graph in blue. And then finally, this function is defined by x squared minus 2x when x is greater than or equal to 1. So that equation, x squared minus 2x, is a quadratic, okay? It'll open upwards because it's a positive x squared. I think the best way to sketch this graph is to factor it to find the x-intercepts. If we let x squared minus 2x equals 0 and solve this equation, we're finding the zeros. We're finding the x-intercepts. Common factor of x gives us x minus 2, and so the solutions would be 0 and positive 2. Those would be the two x-intercepts. So you'd have one x-intercept. Let me change the color here. Let's use this one. You'd have one x-intercept of 0, which is not part of the function. The other x-intercept of 2, which would be part of the function. You can find out where the vertex of this is. It would be halfway between these two x-intercepts because quadratics are always symmetrical. The axis of symmetry always goes through the middle, and the vertex is on the axis of symmetry. So halfway between 0 and 2 is 1, and when x equals 1 up here in this equation, you're going to get 1 take away 2, which is negative 1. So the point 1 comma negative 1 is on this graph, and it would be part of this graph because this graph, or this equation, is valid when x is greater than or equal to 1. So it's a quadratic that'll open up and look something like that. So there's the graph showing all three functions. And now we can answer these questions. What is the value of the limit as x approaches negative 1 from the left? So negative 1 is right here. As we approach negative 1 from the left, the line is approaching this point here where y is negative 1. So that's the value of that one-sided limit. The value of the limit as x approaches negative 1 from the right. So now you're coming down here. and you're approaching the same point. You're approaching a value of y, once again being -1. And so now, because the value of the limit on both sides of -1 is the same, then we can say that the limit as x approaches -1 of f at x is -1, because it's approaching the same value on both sides. What about the limit as x approaches +1 from the left? So as we approach +1 from the left, we're going up this blue line. We're approaching this value here, which is +1. Again, remember, the limit is not asking what is the value of the function at 1. It's what the function is approaching as x gets closer and closer to 1 from the left. Because if we look at 1 from the right, now you're going to be on this half of a quadratic graph that we drew. Getting closer and closer to 1 to the right, the graph is approaching this value here, where y is -1. And now, because you get a different answer when you approach 1 from the left as you get when you approach 1 from the right, then we can say the limit as x approaches just 1 does not exist. And we also say that the graph is not continuous at 1. There's a break in the graph. You have to pick up your pencil or pen and move it to continue graphing. So we again say that this graph, f at x, is discontinuous at 1. Or we can say not continuous. So this next example then says determine where the following functions are discontinuous and sketch the graph. So again, we've got a three-part function depending on what the value of x is. It's first defined by x squared plus 1 when x is less than 0. So the graph of y equals x squared plus 1 is the graph of y equals x squared shifted up 1 unit. So instead of being at 0, 0, it would be at 0, 1. But that point would not be part of this graph because this function is only valid when x is less than 0, not equal to 0. But when x is -1, you're going to get a value of +2. And when x is -2, you're going to get a value of +5. So this is what this side of the graph looks like, something like that. But again, there's that open dot at 0, 1, because this graph is not valid when x equals 0, only when it's less than 0. Then we're told that f at x is defined by 0, meaning y equals 0 when x equals 0. That is a point on the graph. The origin is a point on this graph, the point 0, 0. And then it's defined by x squared minus 1 when x is greater than 0. So the graph of x squared minus 1 is the graph of x squared shifted down 1 unit. Instead of having a vertex at 0, 0, it would have a vertex at 0, -1. But again, this point is not part of this graph because that function is only valid when x is greater than 0, not equal to. Right? We got point 1, 0, that's part of it. And when x is 2, 2 squared is 4, minus 1 is 3. So that's that point right there. And this is what this section of the graph looks like. So the value of the limit as x approaches 0 from the left, this graph is approaching this open point here where y is 1. As you approach 0 from the right, you're approaching this point down here where y is -1. So therefore the limit as x approaches 0 does not exist because the graph is approaching different values as x approaches 0 from the left and right. So that limit does not exist. And again, the graph is not continuous at x equals 0. because to draw it, you'd have to lift up your pencil and move it. So this one's a little bit different. It says g at x is defined by x plus 1 when f at x doesn't equal 2, and g at x is defined by 1 when x equals 2. So that is the point 2 comma 1. The point 2 comma 1, we can start with that is part of this graph. Again, the rest of it is defined by y equals x plus 1 everywhere else. And that would be a graph that would have a y-intercept of plus 1, which actually would not be part of this graph, because when, I should say that y equals 1 only when x equals 2. So it can't equal 1 when x equals 0, because the second part of this tells us that y equals 1 when x equals 2. But the rest of this line will be part of this graph. Okay? Or a portion of it anyways. Actually, no, that's not true. This is part of the graph. Our point of discontinuity will be somewhere else. And we can get that by using the slope. Rise 1 and run 1. Rise 1 and run 1. This is where your open dot would be. Because x cannot equal 2 in this, for this graph. It can only equal 2 when y equals 1. But the rest of the points will be part of this. So this is what this graph would look like. So the value of the limit as x approaches 2 from the left, you're approaching this point where y equals 3. As you approach 2 from the right, you're still approaching the same point where, again, y equals 3. And so because you're approaching the same value on both sides, the value of the limit as x approaches 2, again, is 3. Again, when you find the limit, it's not asking what is the value of the function at 2, because that answer would be 1. But that's not what the limit is asking. It's asking what is the function approaching as x gets closer and closer to 2, and that answer is 3. Yes? Don't wait me, young man.
Sorry. Does the second equation only serve the purpose to say whether it's this graph?
The second equation tells you what y equals when x equals 2. The first part of the equation tells you what y equals when x doesn't equal 2, everywhere else. But when x equals 2, this graph, g at x, is defined by y equals 1. For the what?
For the limit, we don't use the second graph then.
That's right. Because the limit is not asking what is the value of the function at x equals 2. It's asking what is the function approaching as x gets closer to 2. Okay. So we'll stop there. And you can work on those questions. I will post the solutions to Google Classroom. We should be able to go through that quiz tomorrow so you guys can see what you did wrong. So we should be able to do that tomorrow.
I think he's just saying